All right, so let's look at another example here. Here we have nitrogen, and it has 3 silyl groups, okay, attached to it. And so you'd say there's 5 electrons for nitrogen because it's in group 5, 5 valence electrons. SiH3, well, if you add another hydrogen to that, that will make silane, SiH4, which is sort of the silicon analog of methane. So that's going to be stable. So they're 1 electron ligands. So 5 minus 3 times 1 gets you 2. 2 divided by 2, that gets you 1 lone pair. I mean, this is just like ammonia. Ammonia, you might remember, also has this same sort of trigonal pyramidal geometry that is predicted, right? We have 3 ligands with 1 lone pair. That's a tetrahedral arrangement. But then we remove one of those atoms is essentially a lone pair. So we remove one portion of the tetrahedron, and we get that we should have a trigonal pyramid. However, this molecule is not trigonal planar. You can see how we put the lone pair here. It is actually, it's not trigonal pyramidal, it's actually trigonal planar, okay? And this is in the solid state and also in the gas phase. This molecule is planar. And so this is just an example where VSEPR is just plain wrong. There's no way really to explain this using strictly the rules of VSEPR. Now I'm going to show you another kind of empirical theory based on Sterics that you can use to explain some of these exceptions that seem to be sterically dominated. I mean, one thing you can notice here is that these ligands are very big. Silicon's pretty big, and then they have 4 atoms total, right? And so textbooks, a lot of textbooks, unfortunately, a lot of the inorganic textbooks that are commonly used in undergraduate and even graduate courses will say that this has to do with some d-pi, p-pi back bonding between silicon and nitrogen, and this is why you don't see it in the methyl derivative, because you don't have the empty d orbitals on carbon, just because you're not in the right period on the periodic table, but silicon you do. And so you can maximize this back bonding and to make this molecule planar, okay? There's a few things to say about this. The first is that this explanation is relying upon a molecular orbital interpretation of bonding, right? We're outside of the regime of VSEPR here. And so VSEPR has already failed if you use this line of thought, right? If you use this explanation, because molecular orbital theory, as we'll see in chapter 5, is based upon quantum mechanics. So that's a quantum mechanical theory, and VSEPR isn't. So as soon as you start invoking molecular orbitals, you have invoked quantum mechanics. And that's kind of beyond the purviews of VSEPR. So the second thing to say that is maybe more to the point is that this explanation of d-pi, p-pi back bonding is actually completely false. And so if you run modern day calculations on this, you'll actually see that the amount of back bonding here is relatively little. It's almost non-existent. And in fact, that is true for back bonding on most, if not all, main group element chemistry. So modern day chemical calculations have basically disproven this theory and have shown that for main group chemistry, d orbitals and this back bonding idea don't play any role. But it's a very convenient trope to kind of carry along through textbooks. And so that's why you see it even in modern day textbooks, because I guess people didn't, what will we say, fact check their textbooks. And so that's what this say. Yeah, modern day calculations show that d orbitals play essentially no role in main group chemistry. So how can we explain this? This is probably a better explanation. As you'll see, it's still highly empirical. And the best explanation is really just looking at molecular orbital theory and comparing two structures energetics, as we will do in chapter 5. here's kind of an empirical spin-off theory from VSEPR. And this is looking deeply at the sterics, okay? So what you can do is you can actually map out the sterics and see what geometries can work. And so you can look up the radius of silicon, right? The bonding radius of silicon. And then you can say, okay, if it's planar, I'm gonna have 3 circles that look like this, right? And that's gonna give me some open space, sort of this triangular looking open space that has a certain size. And that size is based upon the radius of these circles, right? And you can do some geometry. It actually turns out to be some fairly fun trigonometry. I don't expect you to be able to do it, but it ends up being this 2 times √3 divided by √2 times r silicon. The largest circle that can fit in here has about a value of 0.15, 15% the radius of silicon. So the radius of this circle, the largest circle that can fit in this hole formed from the 3 circles of silicon is about 15%. And so what you can do is, once you figure that out, you can come up with a hypothesis that states that if your nitrogen radius, or whatever your central atom is larger than 15% of the ligand atom, silicon, then the molecule must be trigonal pyramidal, because it can't fit in that hole. So if it can't fit in the hole, then it's going to distort from this highly symmetrical structure, and it's going to bend down and give you the VSEPR predicted theory of trigonal pyramidal. So if you look up the van der Waals radius for nitrogen, it turns out to be about 14.3% that of silicon. So it is indeed small enough to fit in this hole. And so based on our hypothesis, then this molecule, nitrogen, can fit in this hole. And so then the molecule will want to be planar. Okay, and so going back to these structures, so we've kind of proven, and just experiments have proven, the structure on the right here is the actual structure. And so a question that really should be burning in your mind right now is, something's weird, because I drew a Lewis structure here, and I have an octet theory satisfied, right? I have 2, 4, 6, 8, but here I didn't draw a lone pair, right? And so where is the lone pair? I didn't even draw it. And the reason I didn't draw it is because, yes, it's still there. It's not like I just got rid of it. If I got rid of it, it would be a dication, right? It's not a dication. It's still a neutral molecule. It's still following the octet rule. But really, when you draw these Lewis structures, this is a total artifact. That lone pair isn't just hanging out over there, okay? That lone pair is in some molecular orbital. And so in both structures, I don't know where the lone pair is. I don't know where you want me to draw it. It's in a molecular orbital, and I can show you what that molecular orbital looks like, and what all the molecular orbitals look like for bonding. And we'll do that for various molecules later on in chapter 5. But this whole idea of drawing lone pairs is just a fabric of the artifact of VSEPR and Lewis structures. It's nothing more. And so I might as well just not draw it, since I know the VSEPR structure is incorrect. So, why am I then kind of beholden to this VSEPR theory? There's not really a place to draw this that makes sense, okay? The truth is, or the more accurate representation of the truth, as far as we know it, right, is that lone pair is in a molecular orbital that's diffuse across the whole molecule. As we'll see, and many times that's how lone pairs are, okay? All right, so there's some other structures that you can use this same sort of empirical spin-off theory, I'll call it, of VSEPR. And some other things you can say about different structures that are controlled by sterics. So, for example, PF7 2- does not exist. That's not a stable species. It's never been isolated. But the antimony analog can. Why? Antimony is a bigger central atom. And so there's enough, it provides a bigger center sphere point to put these 7 fluorine ligands, right? You have a lot of highly electronegative ligands all next to one another. PF5, that's a stable monomer, but antimony pentafluoride wants to form forms oligomers. Why is this? Again, antimony is going to want to maximize bonding opportunities because it's bigger, and it has room to accommodate more ligands. So it has room to accommodate higher coordination geometries. So these are some examples of structures controlled by sterics. Let's look at TeBr62-. 6 electrons for tellurium, it's a chalcogen. 2 electrons for the difference in charge, right? We have a 2- charge, it's an anion. We gotta count for that. And then we have 6 halogens, right? Halogens are 1 electron ligands, so we go 8 minus 6 times 1 gets us 2. 2 divided by 2 gets us 1 lone pair. And so you end up with 6 ligands plus 1 lone pair. That's going to get you a steric geometry of 7. If you go back to the previous videos and the previous slide, you'll see that the VSEPR geometry for a 7 coordinate system is pentagonal bipyramidal. There's a lot of different options here. There's 2 different options for VSEPR structures. The VSEPR structure, the prediction, what would that be? That would be this one. And so let's go into why. That would be on the one on the left. Why is that? Because the equatorial site here, what's the angle there? It's actually 72 degrees. That's in the pentagon. 360 divided by 5, that's 72 degrees. This is a right angle at 90 degrees. So now with the pentagonal bipyramidal arrangement, the axial ligands are actually the roomiest sites. And so before we had VSEPR predicting, right, when you had trigonal bipyramidal, in that case, you only had a triangle in the equatorial site. So the 120 degrees, that was the roomier site, right? But here, VSEPR is actually going to predict that you have this geometry where the lone pair goes in one of the axial sites and you maintain the pentagon in the equatorial. But what is even crazier is that the actual structure is neither of these VSEPR structures on the left and the right. The actual structure is almost perfectly octahedral, okay? And so it's octahedral, which looks like a steric number of 6. Indeed it is. Where's the lone pair? Where'd the lone pair go? Again, lone pairs are molecular orbitals. VSEPR and Lewis structures are just constructs that are not good reflections of the sort of electron dynamics in a system, okay? So you can do similar math as we did before with the case where we have the silyl substituted ammonia. And this time, the math comes out to be about 0.41. So if your radius, again, you can draw 6 spheres in an octahedral arrangement. You can use geometry. Again, it's a bunch of trigonometry. You don't have to do it. I'm always just going to give, I just want you to know that this concept of can you fit an atom inside a hole that is formed by a bunch of other atoms. And so for an octahedron, that is 0.41. It has the radius of the central atom A has to be less than 41% the radius of the ligands in order for you to get an octahedral structure. If it's bigger, the structure will distort and you'll get one of those geometries based upon a pentagonal bipyramidal steric geometry. And so what's really cool is you can look at different structures and calculate isoelectronic structures and calculate their ratios. And you can see that in general, if you're higher than this 0.41 value that we calculated theoretically, you will then get a distorted octahedron. You'll get the geometry based upon what VSEPR predicts, something based on a pentagonal bipyramidal structure. And so that's true for xenon hexafluoride. It's true in some of these other cases, but you can see it becomes kind of a blurry line. Like in this case, these molecules are distorted in the solid, but in solution, they're more octahedral. maybe there's some more flexibility in solution, and so the more symmetrical structure prevails there. But you can see once you get to cases where you have very small central atoms relative to ligands, so big halogens and relatively small central atoms, then you're getting octahedral cases. Okay, so it's not perfect. Obviously, this is a very, very simple theory, just like VSEPR. It's a spin-off on VSEPR, but it does a very, very good job at making predictions.